Okay, so today's 1.4 and 1.5. We're doing kind of three different topics. One-sided limits, which should go pretty quickly because we've kind of already talked about limit from the left, limit from the right. It's really just remembering notation on that. And then we're going to talk about continuity, which we talked about last year. And then also infinite limits, which I don't think we talked about that last year. So that I'll kind of focus more on. If I looked at this graph that I've given you up here, and I asked you what is the limit at 0, what would you tell me? Yeah, it does not exist. And we've already talked about why. Because as we approach 0 from the right, this side, my graph is getting closer to what number? 0. And as we approach from the left, this side, my graph is getting closer to -4. And we said if those don't meet, your limit doesn't exist, right? So sometimes you're going to see that in a specific type of notation, and we learned it last year. Do you remember the little like exponent looking pluses and minuses that we did? That looks specifically like the limit as x approaches 0 from the right has that little teeny plus sign up here. And we said that would be equaling 0, right? And then secondly, the limit as x approaches 0 with the little teeny minus sign means from the left, and we said that equals -4, which is why our limit wouldn't exist. Now, when I show you that kind of notation, we like immediately think we always have to look from the left and from the right on a graph. We are going to do that sometimes, and sometimes that's helpful to us, and other times it's not helpful to us. And so we're going to kind of reason out when to do it and when not to do it. All right? Sometimes we will sketch, like what we see in example 1. And this is where our piecewise functions and our parent function knowledge comes into play. What is this first equation? What does that look like? It's one of our parent functions. 1 over x squared. This is the volcano. Okay, remember the volcano? And which part of the volcano is it?
Left.
The left side. So there's my volcano graph. What's the second piece look like here? Yeah, it's just a line. Where does my line start?
1.
At 1 and has a slope of 1. Okay, so a little plug for your prerequisites packet. If you know your parent functions, some of this stuff comes very quick and easy, and it should. And then we can quickly say, all right, what is the limit as we approach 0 from the left? What would we say? As we track in from the left and approach 0, where is it headed?
Do not exist.
You could say does not exist. Sometimes from the left and the right, we will actually put the infinities there to say we know whether it's going up to infinity or down. So I'm going to go ahead and say infinity. It's not wrong to put does not exist. From the right, it's approaching what number?
1.
1. Which would mean if I asked you the limit at 0, again, that limit would not exist, right? Now, here's the thing. That is when we've got like a piecewise function split up. If our function is not split and we can actually like find a limit for that, it doesn't matter if it says from the left or from the right. So we talked about limits last year with this little flowchart idea. The flowchart idea says, what's the easiest way to find a limit no matter what? Take the number and do what with it? Plug it in. If you can plug it in and get an answer, that's your answer. If we have to fix it using algebra or different algebraic methods, we talked about it last class, that's kind of our second choice. Graphing's kind of our last one. So even if it's from the left or from the right, if you can plug it in or fix it using algebra, you can just plug in 2 or you can just plug in 0. That still works. So in example 2, even though it says 2, we're finding the limit as we approach 2 coming from the left, I'm not going to go right to a graph because I might not need it. First, I'm going to say, can I plug in 2 to that? Nope, because that gives me undefined, 0 over 0. Next, I'm going to say, do I have a method of fixing this? Yeah, what can I do? I can factor. What factors out of the top?
A different square.
So the difference of squares on the bottom, x minus 2, x plus 2. In order to make it actually like work and cancel for me, I do factor a negative out of the top and flip-flop it. So that cancels. Once that cancels there, the x minus 2's, can I plug into? Sure, what do I get? -1 over 4. And That's the case then where it doesn't matter if we're approaching 2 from the left or approaching 2 from the right. If you get a number back out, you don't have to look at the graph. There's nothing funky going on there. In fact, what we do know is happening at 2 here. If a factor cancels, what is that?
Oh,
It's a hole in the graph. And every time with a hole in the graph in these functions, we're still going to have a limit. And we can find it algebraically. Okay? It also works with trig stuff. It doesn't matter that we're approaching 0 from the right. Sine 5x over 4x, I can still use my special trig limits. Do we remember what the answer to this would be? Well, what's sine x over x?
1.
1 every time. So what do you think this is going to be?
5
5 over 4. Okay? Every time it's going to be those numbers. Okay? There's an algebraic reason for it. I don't need you to go through the algebra of it. It will always work out to these numbers. So if we're approaching 0 from the left or approaching 0 from the right, we can still use our special trig limits. Okay? So on the next page, we have 4 questions here that kind of model this flow chart idea. 3 of them are actually very similar questions to each other. Okay? My first thing on any of these, even if it says from the right or from the left, I'm going to ask myself, can I plug it in? So question 1, can I plug it in?
No.
Not right now. Can I fix it so I can plug it in?
Yes.
Probably, yes. Let's see what we got. We're going to keep the limit as we approach 3 from the left. What are we going to factor? The negative's going to come out.
And different square.
Difference of squares. And I'm going to cancel my x minus 3's. Is this going to allow me to plug in 3?
Yes.
Yep. And I get negative 1/6. That's my answer. There's my answer. That would be the limit as we approach 3 from the left, the limit as we approach 3 from the right, the limit as we approach 3. Done. Now, what if it doesn't work? Let's take a look at 2. Can I plug in 3 right now the way it is?
No.
No, I can't. So my first instinct is to go factor and see if I can fix the problem. This is the limit. As x approaches 3 from the left, I'm going to just reverse the top this time, no factoring, and then factor the bottom.
On the bottom.
All right. It cancels. Can I plug in 3 now? No. Okay, why can't I plug in 3 now?
So you'll get a 0.
I still get 0. Okay, so what's the difference between 1 and 2? 1, I was finding the limit at 3, which happened to be the hole in the graph. I could still find a limit there. 2, I'm finding the limit as we approach 3, which is not the hole in the graph. Where is the hole in the graph this time? Negative 3. Okay, so what is 3 in this graph? Or what am I left with here?
On the,
Okay, it's currently undefined. So we said, if you try to plug it in, it doesn't work. If you try to factor it, it doesn't work. What do we revert to at the end? Look at the graph. This is where our parent functions come in. What kind of equation is this guy?
Like the one with the vertical.
Yeah, it's the one with the vertical asymptote. And which way has it been moved? Where is my vertical asymptote? It's right 3, right? So I've got a vertical asymptote at 3, and then I have 2 branches because I also have a horizontal asymptote at 0, right? My graph looks something like that. Now let's answer these questions. All right, so now it matters that it's the limit as we approach 3 from the left. As we approach 3 from the left, which way is my graph going? Positive or negative infinity? Negative infinity. Now let's answer, because I don't need to redo all of this work for 3 and 4, do I? It's the same question, except it's different limits. But I'm going to use my graph now. So then 3, we're approaching 3 from the right. Where is it going? Infinity. What is this? What do those 2 questions mean about 4? The limit as we approach 3 does not exist. So as you go through, you need to be aware, try to plug it in first. Try to factor. Try to fix the problem. If it doesn't, then graph and see what's going on. Okay? That's our one-sided limits. We're going to move on to continuity. Okay? I think some of us remember this still. We'll do this question first and then talk about the continuity rules. Some of us remember the continuity from last year because you were remembering that when we were talking about the 4 questions, the limit from the left, the limit from the right, the limit, and the f of. We talked a lot about that last year. But just kind of a general concept here. We're going to edit our instructions here. We would like to find A and B so that our function is continuous. Even if you don't remember your continuity rules, what did we say it means for a function to be continuous? Like if you were looking at its graph. Especially a piecewise, what would happen? All of the sections would come together, right? They'd all meet. Now, let's take a look at the graph in 67 first, and then we'll talk about a way to do it without graphing, because we always like to be smart about this. What is this first piece of my piecewise function? Horizontal line that starts at -1 up 2 with a closed dot. There's my horizontal line. What's the issue with the second section? Can I graph it? No. It's a line. It's some kind of line. But with it being an A and a B, I can't actually draw it right now. Our third part is another horizontal line. This one starts at 3, -2. Now, you just told me in order for this to be continuous, I need for my middle line, even though I don't know what it is yet, what do I need for my middle line to do? Yeah, it needs to connect them. Otherwise, it's not continuous, right? So we're going to find A and B so that that line is that. For this particular question, there is kind of an easier way to do it that we're going to talk about real quick. And then I'm going to show you the other way, which will seem a little bit harder, but it will be good in the long run. Okay? What are some ways we can think about finding the equation of that line?
With those 2 points.
Yeah, I can just like find the 2 points and like write the equation of that line. That would be the easiest way in this question. However, here's the issue. Often, and these types of questions are pretty common, often this is not a line. Often this is there's some like parabola joining them. Is it going to work to write an equation of a line on that? No. What if it's like an exponential function? No, right? We have no other ways to write it when it's not a line. So the other way that I want to show you is going to kind of be your long-running way that you want to do these, okay? So just conceptually, what we've talked about is that that line in the middle needs to connect to the first line, and it needs to connect to the second line, right? So what that means for us is this. This line needs to equal that line, and this line needs to equal that line, right? What this gives me is actually 2 equations. AX plus B must equal 2, and AX plus B equals -2. But we also have a little bit more information than that. They need to be equal to each other at a very specific point. Where does AX plus B need to equal 2? Specifically at -1, right? So what can I do with -1? I can plug it in for X. And AX plus B also needs to equal -2 at a very specific X point. What is that X point? 3. So I can plug that in. And what does this give me? Well, it gives me -A plus B is equal to 2. And 3A plus B is equal to -2. What is this called when we have 2 equations and 2 variables? It's a system of equations. Do you remember those? Elimination and substitution.
Yeah.
This is something that's going to come back so often in calculus. We have so many systems of equations, substituting into one or the other. Even though that's a harder way to do this question than just writing the equation of a line, it's the better way to often solve these because if it's not a line in the middle, that's going to be your best way. So this, I will just easily eliminate my b's by subtracting. Negative 4a will equal 4. Therefore, a is equal to negative 1. And then I can plug back in and find that b, that would give me 1 plus b is equal to 2. B is just equal to 1. Okay? So that's telling me that this line right here has the equation y equals negative x plus 1 to make them meet. All right? This is going to come up a lot in your online quizzes. Okay? You'll also have a question like this on your homework, and half the people will walk in and be like, I don't know how to do this. It's exactly like this. All right? Use the same way. Now, we talked about just generally the idea of continuity, making the pieces connect. The calculus version of that is this. In order for a function to be continuous, 3 things have to be true. And this is where we started last year looking at the 4 questions. Okay? 1, your f of value has to exist there. Remember, the pictures that I give you for these are a way of showing when it's not true. So this right here, where there's a hole in the graph with no other closed dot, this is what it looks like when it's not true. No f of c value, okay? Secondly, the limit at that value must exist, okay? So this, again, is a picture of what it looks like when that's not true. Right here, we would be discontinuous at 0 because there's no limit at 0. And then third and finally, we would say not only must we have an f of value and we must have a limit, they must be the same number, okay? And this, again, is a picture of what it looks like when that's not true. Right here at 5, we have a limit. The limit there would be 1. We have an f of value. The f of value at 5 would be 3, but they are not the same number, okay? And so actually on the back of this page, I'm going to go to question 6 first to show you one of the main reasons we learned this and the way we write this in an actual AP exam, and then we'll go up to a multiple choice question after that, okay? This is actually from the 2011 free response with non-calculator. They wanted to show that f is continuous at 0, and this is where our notation and writing and our skills of showing and proving for math come into play. We just said 3 things have to be true, and I want you to learn that process so that you can just write out those 3 things, okay? All right, to show that a function is continuous, I just walked through those 3 conditions. If we want it to be continuous at 0, what's the first thing we said had to be true? It had to have a f of value, right? All right, so let's go find it. Number 1, I must show that I have an f of 0. How can I do that with this?
Plus 0 to the x.
Yeah, I can just plug it in. But which piece do I plug it into?
First one.
The first one, why?
This x equals 0.
X is equal to 0 in that one. So I plug it in. 1 minus 2 sine of 0. Oh, look, there's our prerequisites again.
0.
Sine of 0 is 0. Therefore, f of 0 is
1.
1. That's all you have to show for the first part. What's the second thing we need to prove is true? Okay, the third thing is that this is the same as the limit. So what's the second thing? That we have a limit, right? In a piecewise function, how are we supposed to show that we have a limit? If their left and the right is the same, right? So I kind of need to show, and this is where it goes with my left and right-sided limits, that I have a limit as we approach 0 from the left, and that I show that I have a limit as we approach 0 from the right. And really, what do I want them to be? The same. So in order to kind of save myself some room, I often just write that like this and leave myself a space in the middle to write what that number is. So I don't have to do the limit as we approach 0 from the left, the limit as we approach 0 from the right, and then say that I have a limit. I can just say, here we are, okay? As we approach 0 from the left, which piece would we plug it into? Top or bottom?
Well, top.
Top, why?
Because x is less.
Less than. Have we already done that? Yeah, I already know what that is. That's 1 from the first piece. Okay, so all that's left is for me to plug it into the one from the right. And from the right is we plug it into the bottom one, right? So if I plug in 0 to e to the negative 4x, what am I going to get back out? 1. Why? Anything to the 0 power is 1. All right, so have we shown that the left and the right are both 1? Yep, that's enough to say we have a limit. All right, and then what's our third condition? Okay, and then this is where it feels like we're repeating things. Because if it's you guys, you're like, well, I just said that. But did you actually show the people grading your test that you know that those have to be equal to each other? You did not. So you can either write number 3 like this and say f of 0 equals the limit as we approach 0. So what are we trying to show? F is continuous at x equals 0. One of the things we're going to talk about in like communicating with math is answer the dang question. Sometimes we write all of our math work and we don't answer the question. They want you to show it's continuous. Say that it's continuous. Okay? It's not a lot of writing, especially if you've taken some other AP classes. Some other like AP Stat and some of the other ones, there's a lot of writing. Okay? Ours is more, do we know the word like succinct? We just say what exactly we need to say, but not in a lot of words. Just enough. That's our goal. All right? I'm going to go back up to our multiple choice. This, again, is a released multiple choice question. Okay? It's one of the very common setups where we have these like 1, 2, 3s, and then they have answer choices. 1 only, 2 only. We get hung up on our answer choices. Here's how you need to take these kind of like multiple choice ones. Ignore your multiple choice answers. Decide whether these statements are true or false, and then go look at your answers. Okay? You are smarter than the questions. Don't get hung up on like which combinations. So first off, number 1, f has a limit at 2. I need to decide that. How would I decide if this piecewise function has a limit at 2? What do I need to do?
See if you get the value that
Yeah, like I need to see limits from the left, limits from the right, see if it works. Now, what does it mean? Because this is a little bit different when it's not equal to. What does that mean?
it's like not exactly 2.
Yeah, it's everything but 2. Essentially, this function is everywhere except at 2, which means there's essentially a hole or something going on like that at 2. All right, so let's see. Do we have a limit as x approaches 2 of this? Let's find out. Can I plug 2 in? Nope. Can I fix it?
Yes.
Yes. Now, this is a multiple choice. Do we care about our notes or our notation on this? Okay, I want you to use limit notation where you need it. Do I need it on a multiple choice? I don't. Okay, so I can't plug it in. Can I factor it? Let's see. All right. Cancels. If it cancels, we just talked about this. What do we have at 2? A hole. Do we always have a limit when there's a hole? Yes. Can I now plug in 2? Yes. Do I have a limit at 2 then?
Yes.
Yes. Yes, I do. All right. Moving on. We need to decide if 2 is true. If f is continuous at 2, we just talked about this. 3 things have to be true. We have to have an f of value at 2. Do I have an f of value at 2? Yeah, what is f of 2? 1. Okay, check. Got an f of value. I have to have a limit at 2. And again, I probably wouldn't write this down on a multiple choice question, but I'm helping you reason through it, right? Do I have a limit at 2?
Yes.
Sure do. We just found that in part A, right? That was, what did I get, 4?
Yes.
All right. And then what's our third condition?
They gotta be the same.
They got to be the same. Are they the same?
No.
No. We're done. And then 3, differentiable. Well, this is unit 1. You don't know like anything else in calculus right now, okay? Later on, you will know what differentiable means. It means you can take the derivative of it, okay? We don't know this yet. Since we don't know this, let's see if we can even figure it out even not knowing it, because we're smarter than the test. What answers can we eliminate right now?
A.
Okay, well, can we eliminate A? Is A true?
Oh.
Which of them are
is
true?
true.
Okay, so A is true. What else can we eliminate?
B,
I can eliminate B,
D,
D,
and E.
and E because we know 2 is not true. Oh, and because we're smarter than the test, even though we don't know what differentiable means right now, we know 1 is true, right?
Yes.
So even if you had no idea, guess what? You can figure out an AP question. Yay! We're so good. All right. One more thing on this and then infinite limits and we're done. This one, this cracks me up because this is like Ms. Napier's old notes and it's just like her brain on a piece of, and I'm like, what do you mean by this? I know what this means now, but it took me a moment teaching this. This is just vocabulary, mainly, okay? We talk about removable discontinuities. There's also things called non-removable discontinuities. Because the words are big words, it immediately freaks us out. It is not actually that difficult. Removable discontinuities equals holes. It is a synonym, means the same thing. Non-removable discontinuities equals vertical asymptotes. So you could actually have an AP multiple choice question that says, what are the removable discontinuities in this equation? And you need to know they're asking you for the holes. Or they could say, which discontinuities are non-removable? And you need to know they are asking for the vertical asymptotes. So for an equation like this, you would factor it and say, x squared minus 121 factors into x plus 11 and x minus 11, right? Then, because I can cancel x plus 11, where do I have a non-removable discontinuity? 11 would be the non-removable one, because it's the vertical asymptote. The removable one would be negative 11. They call it removable because it's literally removed from the equation when you cancel it. It's gone. Non-removable is literally, it's still in the equation, okay? Those are very easy questions. That's like pre-calculus, right? But it's just knowing the language there, all right? Last but not least, horizontal and vertical asymptotes for infinite limits. This is a review for us. Might help you in your prerequisites. Ooh. How do you find vertical asymptotes of a function?
If it is only a number.
Okay. Where does it have to be? Where do we get the vertical asymptotes from? The bottom, right? You set the denominator equal to 0. Whatever makes the denominator equal 0 gives me a vertical asymptote, right? How do you find holes in the graph?
That's being crossed out.
Yep, we call that factors that cancel. Okay. So we factor everything. If something cancels top and bottom, that gives us holes in the graph. Whatever is left in the bottom gives us the vertical asymptotes, right? So a definition calculus-wise of vertical asymptotes is this. If you have the limit as x approaches a vertical asymptote in the function from the left or the right, it will be infinity or negative infinity. Let's think about that for a minute. As you approach any vertical asymptote from the left or from the right, won't it be infinity or negative infinity? Okay? Or do we have to say infinities? No. We could put does not exist, right? Now, the reason I wrote it that way is because we're also going to talk about horizontal asymptotes. They tell us something different. Horizontal asymptotes. How do we find those? I'm kind of skipping the first question, though. I'll come back to it.
Like the degree.
The degrees. Remember, this is where we used this memory device. Bobo Button eats DC. No, that's only if you need that, right? But remember, that means if your exponents, your degree is bigger on bottom, you have y equals 0 as your asymptote. If your exponents are bigger on top, there is no vertical asymptote. And if your exponents are the same, you divide your coefficients, right? That gives you your horizontal asymptote. Now, the first question asks, horizontal asymptotes describe what part of the graph? Well, don't the horizontal asymptotes only matter as we continue out all the way to the left and to the right? They kind of describe what's happening on the ends of the graph, okay? So we often say they describe the end behavior of the graph. All the way to the left and all the way to the right. In other words, our calculus definition for horizontal asymptotes is this. They give you the answer to the limit as x approaches positive or negative infinity. Because if x is approaching positive or negative infinity, we're talking about all the way to the left on the graph and all the way to the right on the graph. This is where your graph is going to even out at your horizontal asymptote. And so that's going to be your answer, okay? Why does this matter? Well, knowing the difference between the two helps you find answers to these very, very easily, okay? And let me show you that in example 1. I don't want to have to graph this every single time. I want to be smarter than that. I know that question in example 1, 1 over x minus 1, is one of the ones with asymptotes and branches, right? If I wanted to graph it, I could. But I don't have to. Where's the vertical asymptote for that? X equals 1. Where is the horizontal asymptote for that? Y equals 0. Yes? Okay. So then there are some limits on this one that are going to have very, very easy answers. Because I can picture it in my head, and I know what that rational odd function looks like, and I know x equals 1 is a vertical asymptote, I can answer these two limits without actually graphing it. Think about what that would look like. If we approached 1 from the right, which direction would our asymptote be taking us? Up or down? Up. Infinity. As we approach 1 from the left, which direction would our asymptote be taking us? Down. Negative infinity. And if I asked you the limit as x approaches 1, without asking either one of those, you would immediately say it doesn't exist because it's a vertical asymptote. If you know it's a vertical asymptote, you can answer those questions very, very easily. Same thing here. The minute I am asked about horizontal or the limits as x approaches infinity or negative infinity, I know my answer to those questions is always going to be my horizontal asymptotes. So because I know my horizontal asymptote is 0, my graph is going to be approaching 0 at negative infinity and positive infinity immediately. So these are going to be very easy answers as long as you remember the horizontal and vertical asymptotes, okay? All right, flipping to the next page. We're going to try that like 2 or 3 more times and we'll be done. Now, of course, I've got to make those questions a little bit more difficult because a lot of these have holes, vertical asymptotes, horizontal, all the things. So what do we do on this kind of equation in 2? To start with? Factor, always. We've got x minus 2, x plus 1. How's the bottom factor? X minus 2 and 2x plus 3. All right. What happens first? X minus 2 cancels, so I know there is a hole at 2 something. We're going to find what that is. How do we find the y value of the hole? Plug 2 into the new version, right? So if I plug in 2, that gives me 3 over 7. Okay. What about vertical asymptotes? Negative 3 over 2. Good. What about horizontal asymptotes? I'll skip down here. We're finding all the information right away. 1 over 2. Bobo Botten needs DC. Exponents are the same. Divide your coefficients. All right. So now this is left for me to look at these limits and decide, am I talking about the limit at a vertical asymptote? Am I talking about the limit at infinity? Am I talking about the limit at a hole? Because those are all kind of different things. So when I look at these, I say to myself, oh, look, I'm finding the limit as we approach 2 from the left and 2 from the right. What is 2? 2 is our what? Hole. Do we have a limit at a hole? Yes, always. What is the limit at the hole? The y value of it, always. So because I know the y value of the hole, there's my answer. Oh, the next question is finding the limit at the what? This is the vertical asymptote. Okay, it's not asking from the right or from the left, so what does that mean for us? D and E immediately, because there is never a limit at a vertical asymptote, ever. The last two limits are asking about the limit at infinity, and we said the limit at infinity is always answered by the what? Horizontal asymptote. So what's the answer to both of those? 1/2. So without graphing anything, if you know what part of these equations you're talking about, the whole, the vertical asymptote, the horizontal asymptote, and behavior, you can answer these very, very easily. I'm coming back to 3 as our last question. I'm going to skip down to 4. Okay? Is there any factoring to be done in 4? Yes. What can I cancel? One of my x's. What does that mean?
Hole is 0.
There's a hole at 0. And how do I find the y value of that hole? Plug 0 back in. So if I plug 0 back in, what do I get back out? 0. So if I asked you the limit at 0, you would know it is 0. What about vertical asymptotes? X equals 2. So if I asked you the limit as x approaches 2, what would you automatically say? What's the limit at a vertical asymptote anytime? Does not exist. All right, what about horizontal asymptotes? What case are we in with our exponents? Okay, so because, do we have a horizontal asymptote here? Right. There is no horizontal asymptote, which means there is a slant asymptote. Now, we remember doing those last year. We also remember we don't love them. Yes? Okay. So good news for us. If there is no horizontal asymptote and there is a slant asymptote, let's think about what our graph looks like. Your graph always looked like one of these guys. Right? So when there's no horizontal and there's a slant asymptote, if I'm finding the limit as x approaches infinity, that's tracking this right side of the graph. Where's that headed off to? Infinity. It could be negative infinity. It's possible. But really, what have we said about both infinity and negative infinity? Do they really exist? No. So if you have no horizontal asymptote, what are going to be your limits at infinity? Does not exist, because there's no horizontal asymptote for them to level out at. Okay? They head off to infinity or negative infinity, and they don't exist. Okay? Last but not least for today, we are coming back to 3. Now, have we seen things like 3 before? Not really. This is where we get to have fun in calculus, because all of the rules that we just talked about still apply to this. But it just kind of looks funky. Usually, what do we do on these kind of questions first? We're not actually going to multiply anything. We usually try to like factor and cancel, but there's a root going on here, so I can't do that. But
Square both.
I'm not going to square both. I'm actually going to still factor.
Oh.
Okay, we're going to factor what's under the root. Because if one of the factors under the root is 0, don't I still have the whole denominator equal 0? Okay, so I can still do the vertical asymptote thing. How does this factor?
4x minus 1 plus x minus 1.
It's going to be 2x and, yeah, it's 2x and 2x. Okay, so we got 2x and 2x, minus 3 and minus 1, yes?
Yes.
Okay, so using what we just kind of said, even though it's under a root, can I still say what my vertical asymptotes are? Yeah, it's still going to be 1/2 and 3/2. Because if either of those factors equals 0, the whole denominator equals 0. Now, will we have any holes on this? No, because nothing's going to cancel. So none. Now, here's the even more interesting part. Horizontal asymptotes we've always done by comparing degrees, right? This one's a little bit funky because of the root, right? But its behavior still kind of works the same way. What's the degree on top? 1. And then when you look on bottom, I have the highest degree as an x squared, but I also have a root on it. I can't actually just start square rooting random things. But what this means is because we have a square root of a squared, officially the bottom behaves like an x to the first. So what category would that put us in?
Like, we just use the one in the front.
Yeah, we use our dividing our coefficients because officially this is like the same degree. Now, dividing your coefficients gets interesting as well because my coefficients aren't necessarily straightforward. This one's 1. What's the coefficient of the denominator?
2.
Yeah, it is kind of 2 because it's like root 4. Now, here's the other thing with these. Because it's a root, officially, that's actually a plus or minus 2. There are 2 horizontal asymptotes, one at 1/2 and one at -1/2. So how do I know which one gives me the answer to the limits at infinity? Well, here's the easy answer. If you're doing the limit at positive infinity, the answer is the positive one. If you are doing the limit at negative infinity, the answer is the negative one. As long as there's no negative in front of this part of the equation. Because what does a negative on that part of the equation do? Reflects it, right? So it would switch those answers. So it's always the positive with positive infinity and the negative with negative infinity unless there's a reflection in your graph, in which case it would flip-flop. Okay? Questions, problems with that? All right, we're done.